Welcome and thanks for joining me on this talk on debugging ARM Cortex M systems with GDB. Some of the things we'll be looking over you can see in this overview, and we'll start from sort of the basics and dig into more ARM specific things towards the end. So before we get started, let's just have a quick look at the program that we'll be debugging here. It's a really simple program that just does some printf output. There's a counter, and there's a divide by zero error that'll throw an exception that we can try to debug later. I'm using Zephyr RTOS to build the application here and PyOCD to flash it onto the LVC21-308 board, but you can use anything. It's a really simple C program, and any utility that will flash the target development board is fine. So here you can see the L file that's generated. We'll just erase the chip to make sure there's nothing else on there. And then we'll go ahead and flash the L file that we just built. So now that we have our firmware that we've built and flashed to the device, we can actually start some debugging. And to do that, we first need to connect to the device. So let's go ahead and start up PyOCD server, which we can do with the PyOCD GDB server command. And that'll start the server up for us with the target we specify. And once that starts up, you can see the port here is 3333 for the GDB server on core 0. Now, if we wanted to do that with the JLink tools, we can run JLink GDB server, passing it in a few parameters like using SWD for the interface, the connection speed at 4 kilohertz, using the USB interface, and we have to pass in the device name. And that'll start up GDB server for us as well. In this case, however, you want to note the port number is 2331, which is different than PyOCD. So GDB server is half of what we need, and that's the part that will actually physically connect to your development board with a debugger. The other part that we need is a GDB client, and that client will then connect to the server, usually using TCP sockets. And you can do that locally or remotely, which is actually one of the advantages of GDB, that you're able to debug boards remotely as well. So let's start up our GDB client here, and we'll pass that in the L file that we're going to be debugging, because that's where all of the symbol information will be contained. And we'll tell it that we want to connect to port 3333 because we're using the PyOCD GDB server in this particular case. So now that our GDB client is connected to our GDB server, let's get the device into a known state. And that's going to mean resetting it, halting the device, and breaking at a known point, just so we can start our code execution and debugging session with a clean slate. So here we've reset the device. We're going to set a breakpoint on main, the function main, and then we're going to tell it to keep running. And you can see here we've hit the breakpoint that we just set in main. So GDB exposes all of the classic sort of navigation things you'd expect in any debugger. Step into, step over, you can run to a certain number of lines, you can run to a specific location in source code. So just to see how that works, let's open up the serial port on our device just so we can get some printf output. So I'm just using Minicom, and I'll connect to the serial port here. And then in another terminal, we can switch back to our GDB session, and we're still at our breakpoint. So let's just run n for the next code to sort of step over that line. And there we can see our printf output as we've stepped over that line, running from down to line 11 now. So there's a number of variations of these step, next, continue, and tell commands. Something to point out with GDB, though, is that most common commands also have shortcuts. So in this particular case, we've listed C/continue, so you can either type C or the full continue command, and both are identical. But throughout this presentation, we've sort of given the shortcut and the full form notation for a lot of the most common GDB commands. And once you're familiar with GDB, those shortcuts should become second nature. So that brings us to breakpoints, and breakpoints are really the workhorse, obviously, of any debugging session. It allows you to set a precise place in your code where execution will stop automatically. And GDB actually has a lot of quite powerful additional breakpoint commands and options that we can set fairly rich conditions upon which to cause a breakpoint, not necessarily the first time you hit the breakpoint, but you can ignore, say, the first 20 instances of a specific breakpoint. As you can see in one of the commands here, ignore 220, which means ignore breakpoint number 2 the first 20 times that we hit it. So for some very specific errors that maybe only reproduce themselves in given conditions, GDB can actually be quite efficient to sort of quickly hit those problematic points. So let's have a look at how that works in practice. We previously set a breakpoint, so we can type info breakpoints to see a list of our breakpoints, and there's only one defined, which we set at main. So let's delete that. Let's just get rid of delete number 1. Check the info breakpoints again, and we can see that we've got none of them now. So let's set a new breakpoint in main.c, and you can specify line 14, for example, of that file. So we've got a new breakpoint, C to continue, and we'll continue execution, and there we've hit a new breakpoint. Checking our serial output again here, we can see that this print statement hasn't been run yet, so N for next. We'll step over that, and now we should see that print F output, and there it is. So you can see that the breakpoints are obviously functioning like we expect. So info breakpoints again will show us that breakpoint that we've just set. We can get rid of it if we want, because there are a limited number of hardware breakpoints available. GDB also supports something called conditional breakpoints. So let's have a look here. Let's set a breakpoint in main.c on line 12, only if the variable I is greater than 20. So we can see our breakpoint is set. Let's see what details we get. So stop only if I is greater than 20. So now we'll want to continue. We hit our breakpoint, and let's check the value of I just to make sure that that works. So I equals 21. That's already quite powerful, but let's say we only want to hit a breakpoint after a certain number of times, like after 20 times. So let's get rid of this old breakpoint, type info breakpoints. We've got nothing left here. Now let's set a new breakpoint again on line 12. B for breakpoint. So there's our breakpoint. Let's see what it says. We've got just a normal breakpoint. And we're going to say ignore number 5 the first 20 times that breakpoint fires. So enter. Now let's continue. And we've hit that breakpoint. Let's check the value of I, so 42. So you'll definitely want to familiarize yourself with a lot of these commands because they'll be some of the most common ones that you'll be using. So that brings us to watch points. Now watch points are a much more powerful version of breakpoints because they will evaluate a certain number of conditions, or they will watch until a specific variable, for example, is changed or accessed. Now that can be very powerful, for example, for waiting for a specific stack address or something to be changed or exceeded. The fallback or sort of the drawback of watch points, however, is that they're extremely slow. So basically every instruction needs to be analyzed by the debugger when you set a watch point. So they're extremely powerful, but they're not terribly efficient. So you need to sort of weigh your options when you're choosing between a breakpoint and a watch point. For certain kinds of problems, however, watch points will definitely give you a lot more control over the debug experience. So let's see how this works in practice. So let's check if we have any current breakpoints. We do, so we'll get rid of the old ones. And now we're going to set a new watch point on the variable I. So continue. And you can see as soon as I is changed, we hit the watch point or the breakpoint with the old and the new value. So let's get rid of that one and try something different then. Let's say we want to watch the variable I only if I is greater than 50. And you can put quite rich conditions here with watch points in particular. And see, we've hit that again. Now, watch points are quite powerful because you can also look inside, for example, maybe structs or arrays of objects at very specific items, or you can look at a register value by pointing to a specific memory address. And generally, these can really help you trying to sort out memory access problems, or to know at least when some value is being changed in memory. So what about when we want to know something about our system state? That can be the arguments passed into our function, the current state of variables, local or global, the state of the core registers on our Cortex M system. That's where the info command comes in and is quite useful. And you can list all of these things by typing info locals, info variables, info args, info registers. And this is the same command we've been using to check in breakpoints and watch points as well. So this is something that can be quite useful just to know once you hit a breakpoint exactly what's going on in your system at that particular moment and what the state of all of the variables are at that given moment. So let's have a look at how this works in practice. We can type info locals to get our local variables, info variables to get a list of all of our variables, info args. which will be the function arguments. We don't have any in this particular case, and info registers, which will show us the Cortex M core registers. So knowing the device state is important, but something that's also critical when debugging is to know how we got to where we did. And this is where things like stack backtrace can come into play. So backtrace, BT is the shortcut, that will basically show you, it will roll back the stack frames so that you can see the progression of branches and execution in your code to know where you were before you ended up in the current place where you've set a breakpoint or where you've stopped program execution. So let's see how that works. So here we can type BT for backtrace, and we've only got main because we're at the start of our program and we haven't branched to any other functions yet. But let's reset our device to get it into a known state. So monitor reset halt. We'll set a temporary breakpoint on main, so it'll delete itself as soon as it gets hit once. We'll continue. So now we're in a clean state. So let's step into this printk command with the S. So now that we've stepped into the printk function, now we can do backtrace again, and we can see there's a progression from main to printk in the stack frames. So you can see sort of the code flow as we've hit our breakpoint. So let's just step forward a few lines of code, and then we'll set a new breakpoint back in main, just to go back to a known place. So breakpoint main.c and line 14. So we'll continue, we'll hit our breakpoint, and now we can look again at the backtrace and we can see there's only main. So the stack frame has basically gone back to main. So what about displaying variables? That's where printing comes into play. And we can use the print command for fairly rich display of variables or manipulation of variables, or we can even perform sort of calculations on the specific variables or memory addresses, or display arrays of data in a variety of formats. So let's see how that works in practice. So let's just print the variable I. We've seen this before, but let's print it now in hexadecimal with the X code, or we can print it, say, the program counter variable, where dollars is a notation to display or access or manipulate a named register value. So I would encourage you to play around with the print function just to familiarize yourself with it and how you can display the values associated with specific variables or addresses, etc. Complementary to the print command is the examine command X, which you can use to examine memory. So you can show the address of a variable by putting X and your variable name, or you can examine the contents of memory. And there's some overlap between printing and the print and the examine commands, but they're generally quite complementary. And I would encourage you to play around with both the print, the P, and the X command, just so you properly understand some of the differences between them. So whereas one deals more with, say, the content maybe, and the other is useful to determine the address of where something is stored, for example. The two commands also give you very different ways maybe to display the data. So examine can also be used to print the contents of memory, but it has sort of a richer display capability. You can display instructions, or you can format things maybe with a bit more control and precision than the print command is able to offer. GDB is also able to interact with the source code, our C source code or whatever, using something like the list command. So that will give us, by default, the 10 lines around our current location. We can also list specific source like main.c, the main function. And this can be quite powerful in a sense, because rather than just the C files, you can actually access the disassembly of a function like main. So you can see here the assembly source code. In terms of dealing with source code, GDB has a find command, which is extremely powerful, and you can use it to scan a specific address range for a pattern or for a known value. And this could be extremely powerful when you're looking for a specific instance of something, or maybe you want to check, for example, your stack space or your stack memory. If you've pre-filled that with a known value, then you can check during program execution, you can scan for that pattern using the find command, and you can very quickly verify if you've had maybe a stack overflow, or you can check your stack watermark levels, so you can know, for example, up to exactly what point the stack has been used by your application. So maybe you can use this, for example, to claim back some stack memory if you determine that you've defined a lot more stack memory than you need in practice. You can use it for many other things, such as looking for patterns like a string. to find out where that's stored in the image. There's obviously other ways to do that as well, but this is, I think, a command that not a lot of people are aware of, that can save you a lot of time, and it's definitely well worth learning how to use it and playing around with it. Something else that GDB can do well that I don't think a lot of people are aware of, and this isn't a common requirement, but sometimes you have to deal with multiple ELF files when you're debugging a complex system. Maybe you have a bootloader, a secure ELF file and a non-secure ELF file, such as with the project like Trusted Firmware M. Generally, most debugging systems will only allow you to debug one file at a time. And that's true also of GDB, but GDB does have a command called symbol file, which will allow you to sort of dynamically switch the ELF file that is currently being used by GDB, that is used for symbol lookup and just to check associate variable names with addresses, etc. So this is something that can definitely be a lifesaver if you're debugging, say, a Trusted Firmware M project, and you're stepping from the non-secure zone into the secure zone, which will be generally two different ELF files. So you can continue to debug across those boundaries, or maybe when you step into the bootloader, for example, which is perhaps a separate build and also a separate ELF file. So if you're not familiar with it, then that command can definitely make your debugging life a bit easier. So now that we've given sort of the basic theory and common commands, let's look at some practical examples of how to debug sort of one or two really common problems that you'll encounter with Cortex M systems when you're debugging. A common one is ISR stack rollback. So this is where you enter your interrupt handler, and maybe that's a hard fault handler or a usage fault handler or something. And basically the system processor changes state so that what's in the current stack frame that you access doesn't represent where you were just one frame ago, but you want to step back one frame to understand how did I end up in this fault handler. So that's where ISR stack rollback comes into play, and it's a very common operation that you're going to need to do, and it requires a bit of manual calculation generally. And we'll show you a way at the end of this talk how we can speed that process up. But first, let's explain how with GDB we would perform an ISR stack rollback manually. So let's see how this works in practice. We'll first put our device into a known state, so monitor reset halt, set a temporary breakpoint on main, continue. So step into one or two lines of code here, and if you remember, we put an intentional divide by zero error code into our C file. So let's just continue, run to the end, and we should hit the hard fault handler. And there it is. So all of this red code is actually Zephyr's debug handler. It's kind of cheating because we can actually see the address where the error came from, but we're just going to ignore that for now and pretend we don't have that information and try to figure it out for ourselves in using only GDB. So Control C stops execution, and we can see where we've stopped. And so let's check the system registers. And you want to look specifically at the LR register. So because that's going to tell us whether we want to look at the main stack pointer or the PSP. So based on the bit number 2 in this, which is 1 in this case, then we know, depending on whether it's a 1 or 0, but since it's a 1, that means that we need to be looking at the PSP. So let's just print the contents of the PSP. Register, so just dollars PSP. Sorry, let's print the first 8 words at the PSP, and so this gives us our previous stack frame from the PSP, and we want the 7th entry in this, which is the program counter where we were before we entered the hard fault. So if we list the source code for that, we can see exactly the line where our error occurred. Let's say it's not obvious, though, what the cause of our error is. That's where we can look at some fault identification status registers, which exist on the Cortex M. So the 3 main ones are listed here, are the three of the most useful ones. We should start with the system handler control and state register, and that will tell you what kind of interrupt we have: mem fault, bus fault, hard fault, or usage fault. And then based on that, you can look at the HFSR if it's a hard fault register, or for any of the other types, the CFSR. And the CFSR contains basically the sort of sub register values for usage faults, bus faults, or memory management faults, depending on which error you identified earlier with the SHCSR. So you'll want to look at the sort of one subset of this register, and then that will tell you, for example, is this a divide by zero, unaligned access error, whatever the case might be. So that will help you understand exactly why you ended up in this fault handler if it isn't obvious based on the specific line of source code. So let's look at an example of how this works in the real world. So basically we would want to print in hexadecimal or maybe in binary the SHCSR value. And in this case, by looking at the output of that register read, we can tell that this is a usage fault. So based on that, then we're going to look at CFSR bits 16 to 31, which are the usage fault status register. And that's going to tell us that this is a divide by zero error. So let's see that in GDB, just to see how it works there. I'm going to switch to JLink GDB server to read these registers, just because there seems to be an issue with PyOCD, at least the version I'm using, accessing them. So let's start up JLink GDB server first, and then we'll access those registers from a GDB session there. So here we are in our GDB session using the JLink GDB server. So let's just clear the screen here. And let's check the SHCSR, just printing it in hexadecimal, pointing to the correct memory address. And we can see that since bit 3 is 1 here, this is a usage fault. And then we can continue to check the UFSR and other registers to understand that more deeply. So that brings us to the interesting question of how can we automate some of these steps? And recent versions of GDB have integration with Python, so that you can actually write your own scripts and functions directly in Python. And this can be very powerful, especially if you need to parse specific bits or combine different values. And you can write very rich helper functions, basically, things that you would not easily be able to do in a graphical IDE. And I really think this is one of the most powerful features that GDB exposes to you, trying to debug these complex problems on deeply embedded systems. We don't have the time really to go into this in a lot of detail, but hopefully this will at least sort of scratch the surface and you can really dig into it, I guess, for extra credit. Not every version of GDB supports Python, so make sure you're using one that does before you try to use any of these samples. So to start with, let's look at the absolute minimum possible GDB user command. And this is basically a command that you'll implement that you can run inside the GDB client when you're debugging. And so there's just a few lines of code that are required, and you can link, you can follow the bit.ly link here to see a gist where I published this minimal example. And basically this is what you're going to need to do to implement your own command handler. So have a look at that source code, and then you can see how do you load those scripts. And we do that with the source command pointing to the specific Python file. So let's see how that works in practice. We put source projects, just where I have my file, /gdb/scripts/minimal.py. And that's going to load my Python function, then we can run it. So let's just type minimal, and that'll show me my program counter. Now, unfortunately, we're out of time, but I put together a more complex and interesting Python example called fault handler that basically ties together a lot of what we've seen in this talk, including ISR stack rollbacks, checking where you are in the source code, etc. So have a look at the source code. You can see the link to bit.ly here, and load that script. And I think you can take that as a starting point to make fairly complex sort of debugging scripts yourself. And I hope you found this useful. I hope that you'll give GDB a look if it's new to you, or you'll give it another look if you're used to graphical IDEs. And yeah, let us know in sort of the rest of Linaro Connect or offline if you find some interesting functionality that maybe it'll turn into another talk at the next Linaro Connect. So thanks for your time, thanks for your participation, and I hope this has been an interesting use of your 25 minutes. Thanks a lot, and have a great afternoon.